Okay, so we're going to continue with another example. This one is going to be very similar to the last one with some slight differences that are going to be illustrative for us. So using Maple, find the eigenvalues and eigenvectors for the system. So we're going to jump right into it. And I'm going to presume you're going to hit the pause button, use Maple to find those eigenvalues and eigenvectors. It's good practice. So using Maple, we find out that lambda 1 and lambda 2 have particular values. I'm going to go with 1 and 4 in that order. You may find them in the opposite order, but it doesn't really matter as long as you're keeping them straight. And so that means we've got two eigenvectors. One eigenvector is -2, 1. The other eigenvector, should look kind of familiar by now, is 1, 1. So what you'll notice right away is, hey, those are the exact same eigenvectors that we had last time. The only difference is the eigenvalues. Instead of negative like they were last time, this time they're positive. So probably not a huge shock or surprise. That means that the general solution for this is going to look something like y of t equals some constant times e to the lambda 1 t, so just 1 times t, times its eigenvector, plus k2 times e to the lambda 2 t, times its eigenvector. And that, of course, is the matrix form. We don't have to go into too much detail. But I'm just going to point out that if you're given the general form, you can always see your straight line solutions. They're just hiding, right? If you drop those constants, you can see there's straight line solution number 1 and straight line solution number 2 kind of hiding inside that general solution. The other thing that's probably worth noting is that we're dealing with two positive eigenvalues. So positive eigenvalues mean what in terms of the equation? If I let t get bigger and bigger and bigger, what's going to happen to each one of those e to the t and e to the 4t? Well, they're going to blow up. They're going to get huge. So positive lambda means exponential growth. And so what does that mean for our phase plane? What does that mean for our straight line solutions? What does that mean for x of t and y of t? Well, if t gets bigger and bigger and bigger and bigger, then and the e to the power t or e to the power 4t terms get bigger and bigger and bigger, you're going to be talking about just getting huge, 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 and getting further and further away from 0 is the key. So for this solution, as t approaches infinity down at the bottom of the page, both x of t and y of t approach infinity. They're just getting bigger and bigger and bigger. So that means that all non-zero solutions, I don't want to say they approach, that's probably not the best phrase there. I'm going to say they flee the origin. In other words, we're not dealing with a sink at the origin, we're dealing with a source. Right? Something that we would have referred to before as a source because everything's headed away from it. And we can think of it as heading away from it, but along multiple directions throughout the plane. So we can see what that looks like on the next page if we take a look at the sketch of our x of t and y of t. Again, we use the same trick that we did before to be able to figure out, hey, where exactly, which one of these is x of t and which one of them is y of t? Well, again, we have our, when t equals 0, one of the equations equals 2. And so with a little bit of effort, you can see that that bottom equation is going to be k1 times 1 plus k2 times 1. So this must be the y of t equation as well, right? And again, using the initial condition helps us identify which equation we're talking about, which parametric we're talking about, right? Again, you can say that's because x of 0 equals -1, And up here, oops, sorry, let me scooch it up so you can see it. And up here, that's because y of 0 equals 2. So no big surprises there. But at the bottom of this page, we see something that should look pretty familiar. There we go. It looks like the same damn phase plane, but there's a major, major difference. And hopefully you can spot it and it makes sense. All these arrows are pointed in the exact opposite direction. So instead of headed towards the origin, headed towards the origin, towards the origin, everything is headed away from the origin. So you can identify your straight line solutions as well. And so this one was our straight line solution. Excuse me, straight line solution. I don't know which one. What do we call them? Which one was number 1? Which one was number 2 here? Number 1 was with the eigenvalue of 1, so it's going to be this guy here. So this must be straight line solution number 1, and this one must be straight line solution number 2. And just a reminder, this was with lambda equals 1, and up here this is where lambda equals 4. And the same pattern holds in this case as last time. You can tell that straight line solution number 2 is more has more of an impact on the phase plane. Straight line solution number 2 is more influential. Influential, there we go, I can spell, on the phase plane. Since, and again we're going to write it like we did last time, since lambda 2, the magnitude of lambda 2 is greater than the magnitude of lambda 1. So that must be the case. And so down at the bottom of the page, the very last little bit says, hey, in this case, both of the eigenvalues were positive. And so what does that mean for our origin? Well, we have a sink at the origin if both your eigenvalues are positive. Now remember, we're only dealing with both are positive, both are negative, but we're only dealing with real eigenvalues at this point. Okay? So we've got one more circumstance, as you can probably imagine, to look at, which is what happens when you have one positive and one negative. So we're going to take a look at that one in our next video.